Hello, my name is Ishaan Domkundwar, and my project is about improving the ability of transformer models to perform pattern recognition and reasoning tasks. My mentor is Alex Gu, and I chose to research this topic because of my interest in machine learning models and logical mathematics. And I'm presenting from Pune in India. So let's look at the problem. Current transformer models face challenges while tackling logical reasoning and logical mathematic problems. Specifically, cutting-edge LLMs like GPT-4, Claude 3.5 Sonnet, and Llama 3 also face difficulty with logical reasoning and sequence prediction tasks. For this investigation, I'm primarily using sequence prediction as a sort of vehicle to test and probe the model's reasoning and logic capabilities. These logical tasks are some things that transformer models do sometimes trip up on. For example, the prompt on the right shows 3 polygons 4 is 21, 5 polygons 8 is 39, and asks what the answer for 1 polygons 5 might be. So the pattern in this is really quite simple. Polygons is sort of acting as a word that acts as an operator. So 3 plus 4 is 7, which then multiplied by 3 is 21. Similarly, 5 plus 8 is 13, which multiplied by 3 is 39. So the expected answer for 1 polygons 5 would be 18. However, the response from OpenAI's GPT-4o was 11, from Claude Sonnet 3.5 was 9, and from Llama 3 was 33. So I think this pretty accurately shows some of the gaps in the logical reasoning capabilities of these models. Specifically, my research question is, what is the current state of transformer-based large language model capabilities in logical reasoning and pattern recognition tasks? And how can their abilities be improved using prompt engineering? So let's look at the why. I'm researching this topic because of my passion for mathematics, and I think pattern and logic is a big part of maths. And as these models become more prevalent, they're increasingly used to assist with mathematical and logical tasks. And I wanted to evaluate and measure their numerical prediction and reasoning capabilities, again, using logical sequence prediction as a sort of vehicle to do so. I want to focus on improving their capabilities using input conditioning or prompt engineering as far as I can, because these techniques can easily be implemented by a user. And ideally, in the end, I would like LLMs to sort of emulate the capabilities that a lot of online tools that help with logical deduction have, and but with the upgraded capability to understand and process unfamiliar problems. Gathering data. So I used both data sets and smaller sets of data and sequences that I came up with myself to test the initial capabilities of the available models, and also to periodically test the efficacy of the various solutions that I put into place. My primary large data set that I used was the math data set, which was generated in a paper by Google DeepMind. And this data set encompasses a vast collection of problems and problem types, of which I specifically used the sequence prediction part, which was again split into easy, medium, and hard questions. And these difficulty levels help to compare the capabilities of the models for each. Additionally, I also created some sequences that follow unique patterns compared to the data set I used, because the data set had sequences of varying difficulty, but with a similar underlying pattern in each. My experimental setup. So I had to perform a lot of pre-processing on the data set due to its size, and also to align the input data that was going to the models with its desired capabilities. So first of all, the data text files were reformatted using a Python program to make them more interpretable by the future programs that I developed to produce smaller sets of testing data that I could use. Next, of course, I created smaller data test sets with another program that basically randomly went through and selected a specific number of sequence questions, which range from anywhere to 5 to 10 to more than 30 or 40, depending on the test that I was running. And these were then outputted along with their answers. And this output in a list could finally be sent and collected, and using either the ChatGPT chat interface or through code with the OpenAI API for a more integrated and quick implementation, the sequences were passed through to be evaluated one by one. And the answers of each test round were stored and scored against the expected answers from the data set. Now, I passed these through one by one, specifically because when some of these large language models are fed more than one at a time, sometimes their quality deteriorates, especially towards the middle. So for example, if I were to feed 30 or 40 sequences in a single prompt to ChatGPT, its quality may deteriorate when evaluating something. Additionally, the sequences that the model was not able to solve initially were stored separately, and they're constantly added to another file, which I plan to use to evaluate the techniques that I implement and test as to whether they'll be able to solve the sequences that the model wasn't able to at all. So my investigation methodology, again, as I mentioned previously, I'm focusing on using prompt engineering as the main method to improve model performance in these tasks. And prompt engineering is essentially designing and refining prompts or questions to effectively interact with these models. For example, to achieve specific outcomes. And by crafting prompts, we're able to guide models to generate more accurate and useful responses. This involves understanding how different phrasing or structures or types of prompting influences the output and experimenting with various approaches to optimize the results for a given task, which in my case is the sequence prediction. And for my investigation, I looked into various prompting techniques and strategies and experimented with them to test their capabilities. I'm still experimenting with some of them, but these are the main ones that I've properly tested so far, which include chain of thought prompting, retrieval-based prompting, and program-based prompting. So chain of thought is basically a technique to improve the quality of responses from the model by sort of encouraging it to go through the sequence in a step-by-step process. So instead of simply trying to evaluate it automatically and outputting a number for their prediction, it sort of asks the model to think step by step and lay out its steps. The retrieval prompting method is a technique where the model is guided to search for and use relevant information provided in the prompt or previously. So by prompting the AI to retrieve specific data or context, it can help it provide more accurate answers. And this method leverages information to supplement the model's responses to, again, ensure they're more comprehensive and correct. Lastly, program-based prompting involves prompting the model to generate or suggest a formula or program to solve the specific problem, or in my case, analyzing a sequence. So for example, in this approach, I provided the task I provided the sequence that the model was tasked with, and then prompted it to sort of try to create a program or general formula for the sequence that could be used to model and predict the next terms in the sequence. And this technique is useful for generating mathematical formulas or algorithms tailored to specific requirements, and it fits in quite well with the logical reasoning and sequence prediction implementation. So some of my initial results and conclusions. Initially, without any of the prompting methods applied, the GPT-4o model, which I use primarily to test, achieved the following scores across my initial test. It got 80% on the easy testing sets, dropped to 65.5% on medium difficulty, and got 53.1% on the hard testing set. Additionally, the sequences that it couldn't solve and I had stored, once I retested those a few times, it still scored 0% and was not able to correctly predict even a single one. So with chain of thought prompting, I saw that the model immediately had a positive response. And by providing its step-by-step solution rather than outputting the predicted term on its own, the model was able to sort of automatically correct some of the errors that it may have skipped through without the step-by-step thinking when it was trying to simply output just that number. For the retrieval in my use case, examples of how to solve the questions were included in the prompt itself. And using these patterns and how the question was solved, the model is able to sort of synthesize these and apply these to its new unfamiliar task, which it was able to do well. So for example, I gave it a sequence or pattern recognition task with a few, maybe an addition and multiplication task, and then gave it another task that was similar, but with different factors or different operations, and it used its knowledge from the previous task to solve the next one effectively. For program-based prompting, I also observed that this significantly reduced some of the computational errors that the model was facing. And namely, this method helped to reduce some of the hallucinations that the model had. And by creating a specific formula, it reduces the chance of arithmetic errors in the sequence prediction process. And I think this was effective. And I saw that the model reacted to this prompting by following a concrete method to generate the formulas that seemed to work effectively. Additionally, I also limited my data set to only 3 and 4 digit numbers to focus my investigation on more of the logical reasoning capabilities rather than the arithmetic, which would have been more involved with larger numbers and sequences. And I'm currently experimenting with additional types of prompting, as well as a combinations of different methods. And I aim to finally present the most effective approach as a framework to improve the capabilities of these LLMs for these logical prediction tasks. For future exploration, in this investigation, I focused on mathematical sequences and sequence prediction to test and improve the logical prediction and pattern recognition capabilities of transformer models. In the future, more traditional logical statement problems and other types of pattern recognition can also be included, such as the example I gave in the beginning of the presentation, to provide a more holistic overview of the current capabilities of transformers in these logical reasoning tasks. Additionally, testing and improvements can be made without using just prompt engineering with these models. For example, fine-tuning can be run on the testing models to see the effect that it has on their capability to tackle these problems. And models can also be trained from the ground up to specialize in these tasks and compare their performance with available models and their improvements with prompt engineering or fine-tuning. I would also like to acknowledge the help and guidance of my mentor, Alex, who assisted me while developing ideas and throughout the process of my investigation. Thank you for listening.